Hi, welcome to Codex. Our speaker today is Rima Alaifari, who is an assistant professor for applied mathematics at ETH Zürich. Dr. Alaifari's research interests include stability analysis and regularization of inverse problems, tomographic reconstruction, applied harmonic analysis, and signal processing. Today, she will tell us about non-uniqueness of phase recovery from Gabor and Wavelet transform measurements. Take it away, Rima.
Yes, good evening for the people in Europe and good morning to the rest in the US. So thanks a lot for having me. And thanks for the nice introduction, Emily, also. So as the title says, I will be speaking about phase retrieval in a specific setting where we have structured measurements. And by structured measurements, well, we could think of a frame in general, but we will focus on Gabor frames and wavelet frames for this talk. And please, I mean, you can always interrupt me for questions. So I'm very happy to take them. So this is joint work with my postdoc, Francesca Bartolucci, and my PhD student, Matthias Wellershoff, both at ETH Zürich. So Matthias will actually defend his thesis soon. He'll be on the job market, and so will Francesca. And yeah, I'll present joint work with them, and I would like to acknowledge funding by the Swiss National Science Fund. So let me give you an intro. Maybe you are familiar with the phase retrieval problem, so then you just be patient for another 3 slides. So I'll give this intro for people who are not so familiar with the phase retrieval problem and with that specific setting. So what we have in mind, as I said already, is structured measurements. So we want to think of scenarios where we actually have to deal with measurements that, well, can be modeled to be Fourier transform magnitudes, and more specifically, actually, windowed Fourier transform magnitudes. So one setup is coherent diffraction imaging, where the goal is to image very small structures. So think nanoscale, and well, things are much easier when you have crystals, but for non-crystalline structures, you actually need to do computational phase retrieval. And what happens there is that you need high energy X-ray beams that are generated in a synchrotron. So here you have an image that I have taken at the Swiss Light Source at the Paul Scherrer Institute in Switzerland. They're generated there, and they're then shot at the specimen. And what is recorded is essentially Fourier transform magnitudes. So in that process, phase information is lost, and one is interested in recovering the phase to recover, for example, in that setting, an electron density. To make the problem a bit easier to solve, one tries to introduce redundancy. This can be done with masks, or what I want to talk about, or a setup that suits our mathematical problem a bit better, is tychographic imaging. So redundancy here is actually introduced by not having the X-ray being shot directly at the object as it is, but to have a sliding pinhole. And so we're like windowing around this object, and what we're actually recording is a windowed Fourier transform magnitude, essentially. And hopefully with redundancy, things become easier to solve. So here's the mathematical formulation. Suppose let's say we're in Hilbert space and we have a measurement system, and we want to ask when a signal can be stably and uniquely recovered from not the frame coefficients, but only the magnitudes of the frame coefficients. So here really the problem is that we've lost phase information. And of course, the introduction of the magnitudes makes it a nonlinear problem. So this is here the hurdle. And in addition to X-ray diffraction that I told you about, another application, and maybe the most truthful to what we're doing, is audio processing. There you have different applications. Actually, I just learned last week by Bernhard Bodman that the origin of phase retrieval and audio processing is the cocktail party problem, where you're trying to separate different tones. Another application is the phase vocoder, where you want to modify an audio signal. So think of time stretching or pitch shifting an audio signal. All right, so what do we want to do? Here is the setup a bit more specifically. We have a Hilbert space, we have a frame for that Hilbert space. And there are trivial ambiguities that we have to exclude to make sense, even to ask about uniqueness and stability. I mean, in this talk, I'm focusing on the question of uniqueness. Then the trivial ambiguities are that we can't recover up to a global sign factor or a global phase factor. So here we're either in the real valued setting or in the complex valued setting. We have to exclude either the sign. So for example, if you have measurements, then F and minus F, you will never be able to distinguish from phaseless measurements. And in the complex valued setting, then you'll have a global phase factor always. And we can formulate phase retrieval as inverting this operator. So up to this global phase factor. So we're thinking that quotient space, and we would like to think about the inversion of this operator. And so the distance naturally now is defined as the infimum here, where we allow any phase factor, global phase factor, right? So F and minus F would have distance 0, right? And we will, as I said, I will speak about specific frames, so the Gabor and the Wavelet frame. I will use VG as an abbreviation of the Gabor frame. So the Gabor operator, short-time Fourier transform operator. So what is that? What I'm doing is I'm taking in a product of the signal with time-shifted modulated versions of a window. So here, the short-time Fourier transform always depends on the choice of the window G. So here I'm time shifting and modulating that window, and I'm taking in a product. So maybe you are familiar with that, then this is how you would write it. You would write a time shift by X and a modulation by Y, and taking in a product like this and defining this for all X and Y and R. So VGF is a function that lives on the has the coordinates either in R2 or in the complex plane, as you want to think about it. And the wavelet, we define it to be, so here the continuous wavelet transform. Again, we are taking in a products, and now we have a wavelet there that we are dilating and time shifting. So this is how we would think about it. We have a dilation. So this is our window psi or wavelet, and it gets dilated by a factor A and time shifted by B. And dilation is a value in R plus, and we take it over B in R. And so the question we want to ask is, can we identify windows for the short-time Fourier transform or wavelets for the wavelet transform? And think about index sets here and function classes so that we can ensure injectivity. And specifically, we're interested in discrete index sets. All right, so I'll say a little bit also about the continuous setting or also the semi-discrete setting, but the most interesting or the most unexplored, although also there are not many uniqueness results, for example, for the wavelet transform in the continuous setting, but the discrete setting here is what I want to focus on. Okay. So let me start by actually not talking about wavelets or Gabor transforms, but here is a classical result that we employ in our work every now and then, and I think it's nice because it kind of gives you a flavor of phase retrieval problems. So here, this is, first of all, this is a remark that this is a sign retrieval problem, so nothing complex valued at all. What do we want to do here? We have a Paley-Wiener space. So here, Paley-Wiener of omega, we consider functions in L2 that have compact support in Fourier in minus omega omega. So here it's B half, and we consider real valued functions. that have compact support in the Fourier transform, so they're band limited. And we ask, what if we only record the unsigned samples? And this is work by Gabor Thakur, his PhD thesis, was a student of Ingrid Dobeshi. And what he found is that actually, if you oversample by twice the Nyquist rate, then you can do sign retrieval. So you will recover G up to global sign factor if the function was band limited. So oversampling helps here. And then, we also have this motivation sometimes to hope that we can do things when we oversample, but of course, there is a very fundamental difference between the complex valued and the real valued case, but still. All right, so let's talk about wavelet phase retrieval. So first of all, you can do a little bit when you extend Gabor Thakur's result to, you can extend it a little bit to the wavelet setting, but again, you have to stay completely real valued. So it's a sign retrieval. It's a sign retrieval result, not a phase retrieval result. What I mean by that is that both the wavelet and the signal are assumed to be real valued. The inner products are real, so the measurements themselves are real valued, and you're just trying to retrieve the sign. And you can do that if, well, your wavelet itself is band limited and real valued. So real valued already said, but band limited. And then you can recover band limited signals under some conditions. So you need that your wavelet has good Fourier support overlap, so that you have an open cover of the frequency domain. For example, you could take Meyer wavelets, and then you can do that. So this was actually joint work with Gabor Thakur. All right. Then there is a result by Malat and Walzburger on phase retrieval from Cauchy wavelet magnitudes. So the Cauchy wavelet is an analytic signal. So it is defined like this in Fourier. So what you have is that it's only supported on the positive frequency, so it has no negative frequencies. And what they find is that, well, this is like a semi-discrete setup. Why? Because they only need two scales. So the signals, their wavelet transforms, they only have to agree on two scales. But there is no sampling in time. All right, so this is a semi-discrete frame. So the scales are sampled. In fact, you only need them to agree on two scales, but no sampling in time. And the uniqueness result says that if f and g are real valued, what you will recover uniquely up to global phase is the analytic representation of that signal. So what is the analytic representation? Of course, if you have a real valued signal, then you only need the positive frequencies to determine the signal uniquely. So you might as well write it in this analytic representation. So this function f plus is defined in Fourier to be twice the Fourier transform of f, but only at the positive frequencies. However, I would like to remark that this does not give you f up to global phase. Okay, so this is a remark that I have, which is if you look at what happens here, so if you have uniqueness up to global phase for the analytic representation, and you think about the definition of this f plus, right? I mean, its real part is f itself, its imaginary part is the Hilbert transform. What you will see is that f and g don't have to agree up to global phase themselves. So you get global phase retrieval or unique phase retrieval for the analytic representation. If you're happy, if that is enough, then yes, but not of the signal itself. All right. So what we did with Francesca and Matthias was to try to go back to band limited signals and try to state a positive result for band limited signals. And so what we can do is we can consider the Morlet wavelet, or in fact, any wavelet that has finite number of vanishing moments. And then we can state a uniqueness result for real valued band limited signals. And I would just like to note here that while the signals themselves are real valued, the wavelet is not. So it's not a sign retrieval problem, but a phase retrieval problem, because the measurements themselves, they will be complex valued. Okay, so here there's no sampling. This is a continuous frame, so the continuous wavelet transform. It's already late over here, so yeah, I hope I wrote continuous correctly. Yeah. So continuous frame, no sampling. So if the wavelet transform really agrees on the entire half plane, then yes, you do get uniqueness. All right, and I would like to sketch a little bit the ingredients, because it's actually quite neat, and maybe that gives also some insight. So, oops. So let me try this. So what are the ingredients? So as I already said, the Morlet wavelet has a finite number of vanishing moments. So Morlet wavelet has a finite number of vanishing moments. So psi hat of 0 is 0. Okay, and then actually already you have that psi hat of psi divided by psi in the limit as psi goes to 0 is non-zero. Okay, so then what one can show is that in norm, as the dilation factor goes to 0, f prime will converge to 1 over a, the wavelet transform, where we fix the dilation a. And this goes to 0 in the limit. And then the other ingredient is that this function, the wavelet, where we fix the dilation, and you can multiply this by n factor a to the minus l for L a natural number, this is also band limited. Why? Because actually here we've just convolved f with a dilated version of the wavelet. So here a denotes dilation by a. And what I mean by the hashtag is that we change we flip the function and conjugate it. Okay, so why is this? So this is true for every a in the upper positive number. Why is this helpful? Because this is a reproducing kernel Hilbert space. So norm convergence will actually give you pointwise convergence. So this 1 over a wavelet transform of f, where a is fixed, this will converge pointwise to f prime. Why is that helpful? Well, because now suppose we have two functions, okay? So suppose we have two functions, and we know that a to the minus l wavelet transform of f with a fixed converges pointwise to, let's say, the nth derivative. Here we just work with the first derivative. And we know the same to be true for another function. Then, of course, that's also true for the absolute values, right? And now I know that the absolute values of the wavelet transform agree. Okay, so let me do it like this so that you can still see the writing. Then what we have is that in absolute values, these derivatives agree, right? And the derivatives are, well, they have to be analytic, and they are also real valued if the function itself was real valued. Okay, so I say this always because I'm thinking of the analytic extension of this function, and then it's on the real line, it's real valued. Okay, and then we can employ Garoff-Tucker's result that says that actually if we have an analytic function that's real valued, then we can do sign retrieval. Okay, so actually these functions, they will agree up to global sign. Okay, but these are only the derivatives, not the functions themselves. So what we get is that f minus or plus g will be a polynomial, right? And we know that it's of degree L minus 1. But because the function, I mean, this has to be in L2, it has to be the zero polynomial, right? All right, and then what we can do is we can also find a sampling result. I mean, I promised that there will be some discrete index sets, right? So what if we want to think about sampled version? The answer is indeed we can state a uniqueness result for a wavelet of a finite number of vanishing moments. So here we have a sequence of scales, so finer and finer scales. And well, the time, so the time sampling here really depends on the bandwidth of the signal. And if we do this, then we get uniqueness. So what happens here? I also want to quickly give you an idea of how to do that. So actually, if you follow the arguments from the proof in the continuous setting, what you will find is that the derivatives will agree in magnitude. So for the Morlet wavelet, L is 1, so the first derivative. But you can also do it for more vanishing moments. Okay, and well, then what I have is that these functions are the squared magnitudes are band limited functions, but L1 functions. So I call this Paley-Wiener 1. It's in the Paley-Wiener 2 space. So this is L1 with compact support in Fourier. Then I can employ a standard sampling theorem. So, well, to say that I actually know that the functions agree on the entire real line, and then I can argue as before. All right. Any questions so far? Because we're moving to the short-time Fourier transform now. I don't see the chat. No, there's nothing in the chat. All right, so we can do this later, of course, if there are any questions. So what about the short-time Fourier transform? The short-time Fourier transform is, well, yeah, it's very different, and I think, so at least for me, it's a bit more intuitive to handle than the wavelet transform, I have to say. Doesn't mean that there are more uniqueness results, but I can try to sketch a little bit what we have. So just to remind you of the short-time Fourier transform, this is how it's defined. So you have window, and this is like it's sliding in time, and then you also take frequency shifts of that window. So you're modulating it. And for phase retrieval, we have a very important formula, at least for the uniqueness result, that has been around. I mean, this is not something that has been like specifically proven for the phase retrieval problem, but it came in very handy for the phase retrieval problem, which is the following. It's called the ambiguity function relation. So what is the ambiguity function of a signal? This is the ambiguity function. What you're doing is you're taking the short-time Fourier transform of f, with f itself being the window, right? So now f and g are equal. This would be the ambiguity function of f up to some modulation here. All right. And what the ambiguity function relation says is that if you have the magnitude of the short-time Fourier transform, of course, you can square it. And then if you take the 2D Fourier transform of that, what you recover is the product of two ambiguity functions. One is the ambiguity function of the signal, and one is the ambiguity function of the window. And so this one you know, and well, of course, what we would like to do to recover phase is just divide by this. I mean, that would be great, right? Why would that be great? Because it's straightforward to show that once you know the ambiguity function, you have recovered the signal up to global phase. All right. So an immediate result is that if your window has no zeros, then you have uniqueness of the phase retrieval problem in the unsampled setting. So you really know the short-time Fourier transform on the entire complex plane. So this is the following. Okay, so this is a sufficient condition. We're not speaking about stability here. Of course, it would probably be very stupid to just divide by the ambiguity function of the window. So if you think of the Gauss, then the ambiguity is a two-dimensional Gauss. So you have exponential decay, and you do not want to divide by this. But it doesn't have any zeros. So for a plain uniqueness result, this is actually sufficient. And actually, recent research has been dedicated to the question whether which functions have the property that the ambiguity function is non-zero. And so if you want it to be strictly non-zero, not an almost always result, then this is not so trivial. And so there has been a recent paper by Gröchenik and his co-authors, and they found that there are other functions in the Gauss. So this was unclear for a long time. And one example they give is the one-sided exponential. Of course, if you just want that there are almost no zeros, then Hermite windows would also do, for example. And what we asked ourselves is, again, can we exploit maybe, so can we show uniqueness, or can we relax this condition when we only ask for band limited functions? So for the subclass of functions, or the subspace of the Paley-Wiener space, if we're happy with that, do we really need that the ambiguity function is non-zero on the entire complex plane? Okay, so let me first state some result here. Together with Matthias, we asked this question, and it turns out that if your signals are real valued and they are band limited, then you only need that the ambiguity function of your window is non-zero on one line segment of the complex plane. Okay, so yeah, just one finite segment, line segment in the complex plane. And you can also derive a uniqueness result from samples. And here what we'll do is that the window has the property that its Fourier transform is non-zero almost everywhere on the interval minus BB. Then you can recover from samples. So here again, the bandwidth comes in, right? Okay, so let me give you again some insight in how to do that. So here's a remark. The first being that if you have a function in the Paley-Wiener space, so you have a band-limited function, then its ambiguity function is supported on a strip. So supported on this strip of width 4b. Okay, so what this gives you immediately is that you also need only that your window has an ambiguity function that doesn't vanish on that strip. So you can forget about what happens outside of the strip. So this is an immediate consequence. So if the window G is such that the ambiguity function does not vanish on this strip, then you get uniqueness for band-limited functions. But what we can get is even more. So we only need one finite line segment. So this is the result. So this suffices. So all you need is that the ambiguity is non-zero, where you fix x to be 0 and y is in this line segment minus 2b, 2b. Okay, so then we get, again, this is for real valued signals. The Gabor, the short-time Fourier transform itself is complex valued in general. So this is the result. And well, so why is that? Here, the simple remark is that the ambiguity function of f, if you fix x to be 0, is nothing else than the Fourier transform of the squared magnitude of the signal. And then if you know, so this will give you then uniquely the absolute value of the function. And if two functions agree in absolute value, then we know if they're band limited and real valued by Garov's result that we have unique sign retrievability. All right. So, and in the sampled case, maybe if I do it like this, then you see a little bit more. Okay, so in the sampled case, we assume the window to be real valued. And that its Fourier transform is non-zero for almost all psi in the interval minus BB. So think of the Gaussian, for example, or a Hermite window. Okay, and what we measure is we measure the absolute values of the short-time Fourier transform at points n over 4b, and we fix the frequency to be 0. Then this is actually nothing else than having the convolution of f, oops, sorry, with g hashtag at n over 4b. So there is no modulation because we set the frequency to be 0, and actually the window is real valued, so I actually don't need the conjugation even here. And what we can say is that f convolved with g hashtag extends to a function in the Paley-Wiener space, namely the Paley-Wiener 1. And it's real valued, right? And now you can see where this is going. If, again, we can exploit the result that we know about sampling of band limited functions if we know that the short-time Fourier transform. So actually here there is no complex valuedness. So we can discard all the complex valued coefficients and we just concentrate on these, this set of real valued coefficients. Okay, and then we can essentially say that these convolutions agree up to global sign. And well, so that's the Fourier transform, right? And then if the Fourier transform of G is nice, right? So if it's not zero on the support of F hat, then we can do that. So you see, there is a lot really exploiting band limitedness, the analyticity sampling of these, band limited functions, and we need real valuedness coming in somewhere. Something about complex valued signals. So if you actually give up on that setting where you have real valued signals, then you can still say something. What you actually need is you need two lines of the ambiguity function of G where the ambiguity function is non-zero. So in addition to this base segment, let's say 0y, where y is in minus 2b, 2b, we need another one. And it should be nice compared, I mean, it should work nicely with the bandwidth of the signals. And then we still get uniqueness of the phase retrieval problem. Okay, but one line segment is not enough anymore. So I'm just, do I still have, like, how much time do I have? Maybe, is it 10 minutes? Yeah, okay, then I can,
10.
Perfect. Yeah, then I'll give you this, this last insight for, well, almost last. So here, suppose we have two parallel lines. Again, I'll let you see the result actually. Yeah, so two parallel lines. In the time frequency plane. Okay, and on these, we have that the ambiguity function is non-zero. Okay, so so this is non-zero and this is non-zero. So actually, I'm just rewriting the result, but you're seeing it now anyways. And this is for almost all y in this strip. I'm not going to rewrite it, but you see it actually here. So this is the precise statement. And what we get from that is, as before, the absolute values will agree. And this was enough in the real valued setting. In the complex valued setting, this is not enough, right? You cannot recover up to global phase just by having that. But if you have the second line segment, then you will also have that certain products agree, namely the product of F with its shifted version by this factor C that we introduced. All right. And now these functions F and H, they are analytic, they're entire functions. So if they're entire, then we must find a parameter T naught such that we won't hit zeros by looking at the set where we have, so we make steps of size C, right? And there must be a T naught that we can choose that is this shift so that we won't hit any zeros in that set, right? And actually we want to choose it so that jointly there won't be any zeros, neither for F nor for H. This is just because we know how the zeros of entire functions will behave, and then we can do phase propagation. So we can say that, in fact, f of t naught plus nc will agree up to global phase on this discrete set with H. Okay, so there will be some alpha in R. And then we can just employ the sampling theorem, right? So F and H are band limited, and the sampling theorem does the job for us. But it's really essential to have both. So to have two segments in time frequency. All right, let me tell you now about a negative result. So I tried to state some positive results, and now I want to conclude with a negative result about Gabor phase retrievability. So actually, for a long time, we were hoping that there is some critical density. So if you think of a Gauss window, the nicest case you can think of, and you just oversample this frame like crazy, that at some point you will get uniqueness, because we know that the continuous setting is unique, right? We said that if the ambiguity function has no zeros, we have uniqueness. The ambiguity function of the Gauss is very nice. It is a Gauss, a 2D Gauss, so no zeros. So you have uniqueness for L2, for the general class of L2, if you don't sample. And we were hoping that there is a critical density for which you can get uniqueness from samples. So are there sufficiently fine lattices lambda so that this phase retrieval operator is actually injective for functions in L2? This was our question. And we tried really hard for a very long time to show that there is such a fine lattice. And then actually, together with Matthias, we were able to find that this is not the case. So this is really was really hard work by Matthias, who did very nice calculations and came up with counterexamples. So actually, if you choose equidistant parallel lines in the time frequency plane, and the distance between those parallel lines is the parameter given by the parameter A, then you can always cook up counterexamples so that the magnitudes of these Gabor transforms will agree in magnitude on these parallel lines, but the underlying functions, they don't agree up to global phase. So here is a plot of these functions that you can cook up for a rectangular grid. And so first we'll actually look at parallel lines. If you have counterexamples for parallel lines, then you also have them for the grid, for the lattice itself, if you also sample the other direction. And as you can see here, you can even choose them to be very nice, and they're real valued. And in fact, this is a sum of two modulated Gauss. Having said this, so how do you actually choose them? So what you do is they do agree up. So on this, I said it's a set of equidistant parallel lines, the set S. There the measurements agree, but the roots of f plus and f minus, these two functions, they don't coincide. And you can cook up similar counterexamples for, so here you can take rotations of the time frequency plane and also shift it by a factor lambda. And you can always create such counterexamples, and they might then no longer be real valued, but you can still do it. So this phase retrieval operator, if you think L2, okay, for the Gabor transform, so here our window is the Gauss. So this is actually never an injective operator. And let me just conclude by saying what the main ingredients here are. So you can show it directly by exploiting all the nice properties of the Gabor transform, namely that there's an underlying Bargmann transform, and you have analyticity and Hadamard's factorization theorem and so on. But what you always need is the covariance property of the short time Fourier transform. And what we then found out was that you can shorten this a lot by acknowledging that the Gaussian is invariant under the fractional Fourier transform, and this shortens the proof considerably. So under fractional Fourier transform. And there has been a recent paper by Gross and Lear showing that you can also cook up counterexamples when you don't take the Gauss window, but more very general window classes actually. All right, with that, I would like to conclude. I would like to thank you a lot for your patience with me and for being here today. And I'm very happy to take questions.
All right, let's thank the speaker.